Hello, my name is Goksel, and I'm going to present you our latest work about inbound telemetry through programmable data planes. So this is going to be the outline that I'm going to follow through, and I will spend my majority of time in introduction, and then I will briefly go over our heuristic algorithm and then results and finish with the conclusion. So let me start with pointing out some of the importance of network monitoring. So with the addition of new devices or new services, existing network infrastructure becomes more complex each and every day, and managing them becomes a challenge. And in order to manage them properly, there has to be an efficient network monitoring underneath so that we can provide up-to-date status information as quickly as possible with low overhead to applications that manage the network. So let me continue with the problems that we have observed with legacy telemetry solutions. So in the legacy telemetry solutions, you will observe that a maintainer of the controller will fetch information from every single individual switch periodically, and this period is kind of a low period due to the high communication overhead between the control applications and the switches. Of course, with the introduction of software-defined networks and the improvements on the open flow switches, these limitations are kind of lifted, as the switches can now periodically send information back to the controller. However, the information that's going to be collected is not customizable enough in those switches, in a sense that you cannot introduce your customized protocols or customized telemetry pool freely. And addressing these limitations, there's a new concept called P4, which is a data plane description language that aims to facilitate the customization of packet processing and forwarding pipelines. And what it means is that it offers full-fledged control over how you are going to parse packets to the maintainer. And in that regard, the maintainer has the ability and flexibility to implement any protocols on demand, or you can modify existing ones and tailor them to your use. And of course, this also goes for the available telemetry pool, and it allows you to customize any measurements that can be collected from these switches. One of the applications or the idea that has emerged from the P4 organization is called inbound network telemetry. The idea behind this framework is you are going to program the data plane in a way that they recognize certain types of packets, and they can insert their own telemetry headers to those packets when they observe them. So in this figure, these packets are called probe packets, and they follow a certain sequence of switches in the network, and which is called INT-path. So whenever switches observe these probe packets, they will insert their own telemetry headers, and this packet will grow. And when it arrives at the destination or the last switch in the path, the last switch will going to forward the telemetry packet back to the controller. So as you can see, this actually fixes one of the problems with the legacy telemetry solutions, which is the communication overhead between the control application and the data plane. Since the inbound network telemetry actually allows a certain package to carry multiple information of multiple switches, so that you can actually minimize the control overhead. However, there are certain design problems in using the inbound network telemetry correctly or efficiently. So one of those problems is how many paths would you like to generate? So you can actually define any number of paths that can traverse in the network so that you can actually obtain the holistic view. However, there are certain problems. For instance, if these paths are too long, in this case, we have a 26 switches long path here from A to switch Z. If this path is actually too long, you will observe some inconsistencies in the age of telemetry information being gathered. And what it means is that these packets are stored in the network until they arrive at the controller. And therefore, when you insert the telemetry headers to these packets, they will arrive at the control after certain delay, right? And therefore, there might be some cases where if these paths are too long, the information being gathered in the earlier switches will refer to an older state of the network, while the newly gathered ones will refer to some other state. And therefore, this will create some inconsistencies for your monitoring applications. So in ideal world, you would like to minimize these inconsistencies by achieving timely delivery and using multiple paths that can cover the network. And what timely delivery means is that you would like to have paths that will arrive at the controller around at the same time, so that you can actually obtain the measurements within a certain time period in which the results will refer to the same state of the network. And also there is a problem of redundancy. And what it means is that whenever these paths intersect on certain switches, you will collect measurements of duplicate measurements in essence. However, when you do so, you are actually reducing the amount of space that you are available to you, which is maximum transmission unit that is defined over the links, right? So if you carry too much duplicate information, you will actually reduce the available telemetry space to you, and you will not be able to carry too many information or too much information, and you will not be able to provide high granularity information to your monitoring applications. So in that regard, if you minimize redundancy, you can actually maximize the amount of information or amount of different information that can be carried and fetched from each individual switch. So in our latest work, we have proposed a graph-partitioned in-band heuristic targeting these three requirements. And those requirements are: how can we minimize the overhead, and how can we balance the path so that they can arrive at the controller around the same time, and also how can we minimize redundant information. And in that regard, we accept a certain parameter called k, which defines or sets the maximum number of paths that are going to be generated. And in this work, we generate or partition the graph in a way that we generate simple paths that contains no loops, and also they are as disjoint as possible while maintaining their balance in the layer lengths, since they correlate to how much time they will spend in the network and how fast we will deliver them to the controller. And if their lengths are similar, what we will observe is that what we can achieve is the time of delivery. And you can find more information in our latest publication that will be available later in this year. So let me briefly go over some of the important results that we have observed in this work. So essentially, as I mentioned, we have a variable called k, which defines or sets the maximum number of paths that are going to be generated by our algorithm GP. And if we set k to 2, what we are actually doing is we are generating minimum number of paths, and with 5 we are generating maximum number of paths. Regardless, what we observe is we have maximized the balance of the paths, and we are actually minimizing the length deviation of these paths, and we can achieve the time of delivery. And we also compare ourselves with the earlier method, which was published back in 2019 in Infocom. So earlier algorithm actually fails to generate the balanced paths, and which will cause some inconsistencies for the monitoring applications. In the right-hand side, we have how fast these algorithms can generate certain solutions that cover the whole network. What we observe is that the GPN can actually deliver the results under 2 seconds. And why it is important is that you would like to run this algorithm multiple times and probably frequently as the network changes. And therefore, you would like to have a fast and efficient network monitoring framework or the INT-path generator, so that you can actually generate paths that can cover the network and deliver timely results. So in conclusion, in this work, we have defined 3 requirements to achieve efficient network monitoring using in-band network telemetry. And in those requirements are minimize control overhead, concurrent report delivery, and minimize redundant information. And in our latest work, we have actually improved what we have done with our heuristic, and we showed the importance of these requirements via simulations. And also during the simulations, we have observed some challenges of using in-band network telemetry, and also proposed certain solutions addressing these challenges. Since it is not published, that I'm not going to go much into detail. However, if you ask me, I can do so in mail or in this presentation as well. So if you have any questions for you, please ask them, and I'm really honored to give you this presentation, and thank you so much for listening.